Hello, so in this lecture, we're going to start looking at reactions of transition metal mediated processes, like the typical types of reactions. And so broadly, we can kind of classify these as ligand association dissociation. And those are technically separate processes, so maybe I can list them separately. And then we have oxidative addition. Reductive elimination. Oh, addition. Migratory insertion, and then finally beta elimination. Okay, so we're going to look at each of these reactions now, examples of them. And so the things to note are that they kind of go in pairs, where ligand association goes with ligand dissociation. And these are kind of classified as ligand substitution reactions. Now, similarly, the next four reactions come in pairs, where oxidative addition, reductive elimination, and then migratory insertion and beta elimination are reverse of each other. Or you could say they're opposite processes. Where, for example, oxidative addition is going in one direction of an equilibrium arrow, reductive elimination is going in the opposite direction of the equilibrium arrow. So let's start with ligand substitution reactions. So ligand substitution reactions are required to start most transition metal processes. Okay, so let's take, for example, a complex like titanium. And so this is going to have two PME3 ligands and two CP ligands. I'm just going to write those as CP as opposed to writing a 5-membered ring with with a negative charge. Okay, so the titanium is in the +2 oxidation state. The complex is overall neutral charged. And so there's a few ways to count electrons, but we've done those, and we find that this is a 16 electron species. Now, what we want to do is we want to let this react with an alkene by some process. To do that, we have to have the alkene actually complexed to the metal center. Now, it turns out that we can't fit any more things around the coordination sphere of the titanium. We can't just put a fifth thing on there because we don't have the options available for back bonding, that sort of thing. If we were working in a main group element, a non-transition metal element, we would draw like hybridized orbitals to show there aren't any orbitals available. That picture is complicated by the d orbitals. So what we say in general for this one is we can't fit a fifth thing around the metal within its coordination sphere. So what we need to do is lose something and then gain something. Okay. So what we notice is we're at 16 electrons, and we can count those. We have an oxidation state of +2 on the titanium, and the d electron count is equal to 2 d electrons because this is a group 4 element and we have an oxidation state of 2. Okay, so what we want to do to get the alkene on is we first need to lose a ligand. It turns out that Lewis base ligands are often the first loss. So I'm just going to show as a curly arrow moving from the metal of the titanium to the PME3. That's going to make a new complex it's now 14 electrons. We have a coordination sphere available, and we're further away from the 18 electron rule, and so we have a more reactive complex. I want you to note, though, that the loss of the PME3 only changes the total electron count. It doesn't change the overall charge of the complex. It's still neutral. It doesn't change the oxidation state. That's still +2. And if it doesn't change the oxidation state, we still have the same d electron count on our metal center. The only thing that changes is the total electron count as we go from 16 electrons to 14 electrons because we lost a Lewis base ligand, the PME3. Okay, so now what we can do is we can adduct to our alkene. So I'm just going to have some generic alkene. And we're going to adduct to the titanium center through a pi complex. So what that looks like is the titanium is going to have a PME3. It's going to have a pi complex, which we show as a line hitting the pi bond. There's, back bonding and that sort of thing in there. Now, the thing is, we still have an oxidation state of +2 on the titanium center. We still have d electron count of 2 electrons, and our total electron count now is back up to 16 as we've accepted the pi complex as sort of like a Lewis base ligand, right, as a 2 electron donor. The charge in the complex is still neutral, but now that the alkene has been bound to the metal center, we can actually start to do chemistry on the alkene, whereas before the Lewis base was sort of sitting there protecting the metal, I guess, to avoid some unwanted oxidation or reaction with water, that sort of thing. Now we've done a ligand substitution reaction, but that wasn't one of the 6 reactions. It was a combination of the 2 reactions that we had listed earlier. The first event is a ligand dissociation event. Hopefully the nomenclature is not too troubling for you. We've lost a ligand. Okay, we lost a ligand and our total electron count went down. But then in the next step, we gained a ligand, and that's the ligand association event. It's typically the case, not always, but it's typically the case, especially for complexes that are at 18 electrons. We need to first lose a ligand before we can gain a ligand. Okay, now it's not always the case. Sometimes there are ways to associate, then dissociate. So we're going to do some chemistry, make something new, and then we typically have to lose that species that's adducted by way of a few processes. Ligand dissociation could be one of them. Excuse me. Okay, so let's go ahead and that's sort of ligand substitution. It's dissociation association with a new ligand. Let's go ahead now and consider the next reaction in the series, which is going to be oxidative addition. So oxidative addition is a profound reaction. I mean, we've seen it before, but it's just kind of remarkable that this type of chemistry can happen. But basically what happens is we take our metal, which I'm just going to write as M0, because this can happen with main group metals, it turns out, which we've seen actually. And we're going to let that metal react with some combination of elements, generically X and Y. And what's going to happen to the metal is it's going to add or insert itself between the covalent bond connecting atoms X and Y. What happens is now X and Y are both simultaneously attached to the metal. For this to work, we now have added 2 monovalent ligands onto our metal center, and so our oxidation state has been adjusted to be +2. Okay, so what's important to note here is that the metal, it doesn't have to be in a 0 oxidation state. It's just allowing me to show you that we can predictably observe that the metal will increase its oxidation state by 2 oxidation state units, I guess. But the metal will insert, we like to use the word add here because we have insertion as something later. And it's going to insert or add itself between the X and Y atoms. And these atoms could be many things. Often it's the case that it's a carbon and a halogen or something that behaves like a halogen. As a result, the metal will increase its oxidation state by 2. So the metal will increase its oxidation state by 2. Hence, this is called an oxidative addition. We've got oxidation state increasing and we're adding. Okay, it's an oxidation event because the oxidation state has increased. Reduction would be something that reduces the oxidation state of something. So the metal was oxidized as it was added. Okay, this is a very important, or this is a practical way of obtaining monovalent ligands. Okay, whereas like Lewis bases are typically added by way of a ligand dissociation, ligand association, just a ligand substitution event. That's how we add up to other Lewis bases or pi complexes. Here we're adding monovalent ligands to the metal center by way of just kind of a net reaction. It's just an amazing reaction. We've seen this before. I keep hinting that we've seen this before in the case of Grignard reagents. Now, Grignard reagents are defined to involve a main group metal, magnesium. It doesn't make the transformation less impressive, even though we're not using transition metals. So this is the reaction that we do in organic 1, where we take our bromobutane, we react it with metallic magnesium, those magnesium turnings, and we do an oxidative addition reaction where the magnesium jumps in between the carbon and the bromine atom. And now that magnesium is in the +2 oxidation state. It went from metallic magnesium 0 into its +2 oxidation state. Now note that we can't do this. I think there were a few years ago, we used magnesium sulfate as the drying agent for the Grignard reaction. And so people would grab magnesium sulfate, which is magnesium in the +2 oxidation state, to do this transformation, but magnesium didn't have the electrons to do the oxidative addition reaction, and so the reaction failed. It couldn't go to magnesium +4. It couldn't increase its oxidation state anymore, and we didn't see the oxidative addition event occur. Okay, so it has to be kind of a low oxidation state, high electron count metal that can accomplish these types of reactions of metal centers. Now, let's look at some common X and Y bonds for oxidative addition. Well, the most common one that we're going to see is C and X. C and X, where X is a halogen, or if you want to get fancy, a pseudo-halogen. I mean, just a good leaving group. So while it could be, you know, chlorine, bromine, iodine, it could also be a pseudo-halogen like triflate, tosylate, even N2+. All of these can serve as good, when bonded to carbon, they can serve as good bonds for oxidative addition to occur. Carbon's actually, I mean, it's just the most interesting one, because as soon as we do an oxidative addition reaction with a halogenated carbon, then the carbon is now a monovalent ligand to the transition metal or the main group metal center, and we can start to do chemistry that involves the formation of carbon-carbon bonds, which is what organic chemists really make their money doing. But there are other bonds to keep in mind. The most important other bond would be H and H. Turns out this is prone to undergoing oxidative addition. And we can have H attached to other elements like silicon, tin. We can even have silicon-silicon bonds, these wannabe carbon atoms that people say could form other types of life because silicon looks like carbon, even though that silicon-silicon bond is so prone to oxidative addition. It's just not that strong of a bond. It'd rather be silicon oxygen it'd be hard to make life out of glass. Okay, anyway, cool thought though. You can also have boron, and boron, that's a really powerful one because it allows you to do other types of reaction. Okay, so now what's cool about this is the H2 one is of particular note. Now it's the CX one we'll spend a lot of time on because we can form interesting molecule. But the H2 reaction allows us to do an important reaction in chemistry, which is the palladium catalyzed hydrogenation of alkenes. So we're going to work through that mechanism slowly as we look at these various types of reactions. But if you recall, if we have an alkene and we add H2 to that alkene, nothing happens unless we have some palladium on carbon. And then we get R now, our alkene now bonded to two hydrogens and effectively reduced down to the alkane center. Now, the first step in the mechanism for the palladium catalyzed hydrogenation is we take a mostly unprotected palladium 0 center without its ligands to sort of protect it from oxidation and that sort of thing. And we react that with H2. Now we don't just do, for H2, we don't just do an oxidative addition event straight away, even though I've alluded to H2 being a good bond for oxidative addition. The first thing we do is actually we do a ligand association event. Ligand association will occur to form a sigma complex. It's kind of a wonky one to draw. It looks like a pi complex, except it's just to a single bond. So it's a sigma complex. We have an H here and here. So we have ligand association. We increase the total electron count on our metal center by 2 because we have a new ligand. We go from that to nothing. And remember, the carbon isn't so much of a ligand as it is just an effective way of delivering a small amount of palladium to the reaction mixture. Now, palladium adducted to hydrogen will undergo an oxidative addition reaction. I'm going to write that out. Into the palladium, or excuse me, into the H2 after it's associated. And we now have a palladium plus 2 centered. The complex is overall neutral, but we have 2 monovalent hydrogen H ligands. And you'll notice that after oxidative addition, the total electron count doesn't change. Okay, so the total electron count doesn't change. We're at, we have 2 electrons from ligands. And then we go from that to having 2 electrons from ligands. And overall, it's 12 electrons because palladium is a group 10 element. Because each of the hydrogens serves as a monovalent ligand. Now, what does change though? So if the total electron count doesn't change with oxidative addition, what does change with oxidative addition? Well, the first thing that changes is oxidation state. But if the oxidation state changes, so too must the total d electron count, or the d electrons on the metal center. And d electron count. Okay. So if we look at this, we're at palladium sigma complexed to H2. This has 10d electrons. Okay. After the oxidative addition event, we're at an overall neutral complex, which means you have a +2 oxidation state on the palladium. And now if we have a +2 oxidation state, we have to subtract that oxidation state from the group number to get the d electron count. So this is now 8 d electrons. So we went down in d electron count as we've oxidized the metal, as we've generated bonds with 2 additional monovalent ligands. Okay, so that's kind of one approach. We like to see the sigma complex form, and then we walk into the bond, sort of, to change the oxidation state in the metal. Now, it's important to note that if we don't have, if our metal has 0 d electrons, if our metal has 0 d electrons, we get no oxidative addition. If you don't have electrons to allow our metal center to get oxidized, you're not going to see oxidative addition. Okay, firm rule. All right, 0 d electrons, which happens in the earlier groups of the transition metal, we're not going to see oxidative addition being that productive. Group 10 is pretty electron rich. We have a lot of d electrons. We can give those up. We can undergo oxidative addition fairly easily, which is why palladium is one of our favorite transition metals in organic synthesis. Okay, so I've shown kind of one mechanism where we form that sigma complex and then we jump into the bond by way of an oxidative addition reaction. Turns out there is some evidence of more of an SN2-like oxidative addition reaction. This would be an alternative mechanism for oxidative addition. Okay, so here we have palladium 0, and it can react with, and so this is going to be an SN2-like mechanism. Let me finish my thought there. In an SN2-like mechanism, the palladium 0 could engage a haloalkane, which we know these are good bonds to undergo oxidative addition reaction. And perhaps we could think about the electron-rich 10d electrons as providing at least one lone pair of electrons to do an SN2-like reaction where the palladium adds here, pushing the electrons off onto the X minus. That's going to give us a palladium attached to the R group. Now, when we do that, we actually end up with a complex. This is just kind of weird, but the palladium is now at a +2 oxidation state, and the complex is overall +1. So we have a +1 charge complex, and we've got an X minus that walked away as a leaving group. Well, we can actually neutralize the complex by allowing X minus to adduct to palladium to form a new monovalent interaction. That doesn't do much in the way of the actual oxidation state on palladium. It's still a +2 oxidation state transition metal, but now our overall complex is 0. So what we did is we added to the R group. You could think about that as putting a formal charge on palladium. Now I should be careful. We don't draw formal charges on transition metals, but when we typically have a neutral something attack a neutral something by way of an SN2 reaction, we generate a positive charge something, particularly the nucleophilic atom becomes positively charged. So positively charged something, and that will be then just forever positively charged. That's like the positive charge of our complex that we show here. And then the negative, it just so happens we have a big transition metal that can add up to multiple ligands. And so now the X can come slide back in. That provides that second monovalent interaction. Now, overall, by forming a monovalent bond of palladium to the R and the X, we've done an overall oxidative addition. So we've done an overall oxidative addition on our transition metal without relying on a sigma complex to get there. That'll be about all I'll say at this point about it. What I want to do is just emphasize the most common approaches to using oxidative addition are reactions with halogenated carbons. So what's very common and useful is oxidative addition into CsP2X bonds. And if it's a CsP2 bond, we can't undergo an SN2 reaction. We have to typically do like an addition elimination type mechanism. So that kind of flies in the face of this SN2-like mechanism, and it's a little bit awkward to draw a sigma complex to something like this. So what I'm getting at, though, is the overall reaction, which is typically the starter reaction for some of the most important metal catalyzed processes, is we take our palladium 0 and we react it with, in this case, an aryl bromide or an aryl halide to form a product where oxidative addition has occurred. Now the palladium is in the +2 oxidation state. The complex is still overall neutral, but now we've kickstarted an interesting process where we have a carbon and palladium bond. And that can be done with aryl systems, which were typically mostly unreactive, but here we're interacting with that carbon bromine bond, not the actual aromatic ring. And then we could do the exact same thing with vinyl species where the double bond is directly attached to our halogen. We get the exact same type of species where the palladium has slid in between the carbon and the halogen. It's now +2 oxidation state neutral overall, and it has 2 monovalent ligands, the carbon atom of the vinyl system, along with the iodide, which was our typical kind of leaving group in an SN2-like mechanism. Now, if I need to, I can push some curly arrows for this process. I mean, we'll get into how important the curly arrows are for this type of reaction where we've got an sp2 hybridized carbon atom undergoing the oxidative addition reaction. Okay, so let's first just allow the palladium 0 to adduct to our pi system by way of a pi complex. Okay, so we have ligand association. So the association occurs from the ligand, and we've got a pi complex being formed. Now, one way to depict a pi complex is to have a metallocyclopropane. So metallocyclopropane. This can occur by way of a reaction, or I don't know. It's sometimes people think about it as a different depiction of a pi complex, but it seems like it's going to require a different bonding strategy. But anyway, the palladium is simultaneously bonded to 2 carbon atoms. This is what happens in a pi complex, just that now we're involving different, well, we're just drawing it differently. Okay, so we can now push some curly arrows, namely we could go here to reform a double bond, and then go here to push off the iodide leaving group. That's going to give us a palladium that looks like this, plus an I minus. We're now overall plus charged. We have a +2 oxidation state after this has occurred. Well, really, I mean, the +2 oxidation state kind of starts at the metallocyclopropane, right? Because now it looks like we have 2 monovalent ligands. So some chemistry, I think, has to happen as we go from the pi complex to the metallocyclopropane. It's not just a different depiction. But anyway, we've got some curly arrows in front of us. The iodine can come back in and attack like the SN2-like mechanism, and we get the overall process occurring where we've got a vinyl on one side of the palladium and an iodide on the other side of the palladium. This looks like oxidative addition. Okay, so we've got oxidative addition, but I feel like I want to provide some general thoughts on this before we get like too excited about any one set of these curly arrows. So here are kind of my general thoughts, and that is one, what's important. Let's just start with this before I list these. It's important. It's more important to recognize when oxidative addition will occur. It's more important for that. It's more important to know when oxidative addition will occur and when it will be involved in your overall pathway, as opposed to drawing curly arrows. There are many steps in metal catalyzed reactions where it's like, okay, what are we trying to accomplish with the curly arrows? Sometimes it's super helpful. Typically what involves like the bonds to and from carbon, which I guess is here. But it's often, I mean, in most of the steps, it's more important just to recognize what intermediates will occur. That is, if you look at an overall reaction that involves a transition metal center, it's much more important to know that like the first step is going to be oxidative addition, and then just draw that intermediate, like say metal plus X and Y, and then over the arrow you could write oxidative addition goes to X bonded to metal bonded to Y, which is kind of how we started the lecture. That's much more important than drawing like an SN2 like mechanism. I mean, I kind of like the sigma complex. I mean, some of that stuff is fun to draw, but it's much more important to recognize it's going to occur and know that we're going to involve an oxidative addition reaction, because that's the stuff that gives you the mechanistic insight that we can use the following set of information to help us with. That is, if we know an oxidative addition event occurs, we typically know that we're going to move, or we can say that more electron deficient carbons will react faster. So if we have an electron deficient carbon that's sp2 hybridized, these will react faster. I mean, alkynes react pretty fast too. It's just commonplace to see sp2 hybridized carbons. So electron deficient sp2 hybridized carbon atoms will react quickly. And then after we recognize that it's the electron deficient carbon atom, we note that iodine is faster than bromine, which is faster than chlorine. So iodine's the most, the fastest, sometimes a little too reactive. So here again, bromine hits the sweet spot. And that has to do with kind of sizes of these atoms and bond strengths and that sort of thing. So it's easier to do an oxidative addition into a sigma bond to a huge iodide than it is to do a chlorine atom, even though the difference in electronegativity is stronger between the carbon and the chlorine atom. You seemingly have a more electron deficient carbon atom. So it turns out that we can accomplish this on electron rich carbon atoms, but we have to do something special. So for electron rich carbon atoms, we need to really pump up sort of the nucleophilicity of the metal center, how willing it's able to use its d electrons to initiate an oxidative addition reaction. So for electron-rich carbon atoms, we need electron-rich ligands on the metal center. That's what makes transition metal catalyzed processes so interesting, is that we can kind of tune how nucleophilic a metal center is based on the ligands that we can attach to it. So we have these interesting metals with their interesting electron configurations that provides one aspect of interesting reactivity, and then we can kind of pump up how electron rich these things are, how electron poor these things are based on the ligands that we attach to the system. Okay, so these are kind of three ideas related to oxidative addition to help give us some perspective. So we've hit on ligand substitution, oxidative addition. I'm going to close out this lecture with reductive elimination before I'll wait on migratory insertion, beta elimination for a separate video. Okay, so reductive elimination. This is the opposite of oxidative addition. Now, oxidative addition is a very early step in most metal-mediated processes. Like It's typically only preceded by a ligand dissociation event, and even that's not always present. So sometimes, often, it's the, well, it's hard to know when ligands are associating and dissociating. Those are tough things to characterize. But early steps involve oxidative addition. Conversely, late steps involve reductive elimination. Often one of the last steps in a metal-mediated process. So it's often one of the last steps in one of these metal-mediated processes. Now, what it looks like is, again, it's the opposite of oxidative addition. So let's get that in front of us just really quick. Let's say we've got X and Y, and we react that with some metal. We're going to do oxidative addition. Here, X is now bonded to metal. Whoop, and don't need that little curl. And Y is bonded to metal. Metal now has a +2 oxidation state. Okay, so when we do this, we increase the oxidation state and we decrease the d electron count. Okay, now I'm not going to worry about total electrons because that could have to do with like ligand association and that sort of thing. But then what we're going to do is we're going to do a reductive elimination event where it goes in the exact opposite. The arrows are just going to work opposite of each other. So we have our metal in our +2 oxidation state with fewer d electrons. Now we're going to undergo RE, which is reductive elimination. Reductive elimination, and what we're going to do is let the metal slip out and connect the X and the Y together. So the X is now bonded to Y, and the metal is now in a 0 oxidation state. So here, the oxidation state decreases by 2. Now, if you think about how we calculate total d electron count, we then say that the d electrons increase by 2. Now, total electrons are obviously going to change. So usually, I'm going to put like a usually total electrons decrease by 2 because we've lost 2 monovalent ligands as a result of this, but maybe there's like a sigma complex. I'm not going to worry about this too much. Okay, why would you ever want to do this? I mean, oxidative addition seems obviously useful. We take a transition metal and we start bonding into things like carbon atom. Well, what's cool about it is you could do X, Y, and metal, and we do an oxidative addition reaction. I realize I'm writing down what I just wrote down. Hopefully you can bear with me here. When we do this, we increase the oxidation state by +2. Now what I want to do is, I don't want to just follow oxidative addition with reductive elimination. That's just the reverse process of what I just did. I want to try to accomplish something interesting. So maybe what I could do is I could take my new complex, which has metal adducted to X and Y in the +2 oxidation state, and do a ligand substitution. So I'm going to do ligand substitution. Maybe that's with Z or something. Now my X is bonded to metal still, but maybe now instead of Y, Y is gone, and we have ligand now adducted to our metal center. So we've done a ligand substitution reaction. Now I've got brand new things attached to my transition metal, different from what happened during the oxidative addition event. And this is what happens quite a bit. Typically, what we do is oxidative addition with a carbon halogen. Then we swap the halogen for something else that's got carbon. And then with carbon atom, with 2 carbon atoms, we do reductive elimination to form a new carbon-carbon bond. So here, what this looks like is X, metal, 2+ ligand. The important thing you can take away from this general reaction is that we form a bond between X and something new, some ligand center. But let's assume that ligand center could be something super useful, like carbon atom. Okay, so a specific example would be if I skip the oxidative addition event, just trust me, we can get here, where we've got palladium adducted to an aromatic ring. How would the palladium get adducted to an aromatic ring? Well, it could do an oxidative addition with a halogen atom. But now instead of the halogen atom being adducted to the palladium, we do a ligand substitution reaction and add like an alkyl chain, whatever will cure cancer. Okay, now what we can do is reductive elimination to forge let me get all the spinach. Okay, so now our palladium is in the zero oxidation state, but a product of the reaction is one where we have a bond between an aromatic system and our prime group. This is what makes reductive elimination so powerful, is we can generally form a lot of carbon-carbon bonds. And we regenerate, look at this, we regenerated palladium 0, okay, which was the first thing that we used in the oxidative addition reaction, which I didn't show here. We start with palladium 0, we do oxidative addition, we somehow swap the halogen for something else that's carbon, reductive elimination to form a carbon-carbon bond, regenerate palladium 0. Palladium 0 is a catalyst, which is great because it's super expensive. Okay, so the mechanism for this is, I'm not going to say how much of it is known, but let's just say that I don't want you to worry too much about the mechanism of reductive elimination, save for one point. So don't worry too much about the reductive elimination mechanism. Except in a square planar complex, metal complex, the groups to be bonded by reductive elimination must be cis. So many metal centers can form square planar complexes, which is an important thing to pay attention to. What that means is we have our 4 ligands attached, but they're actually attached in a planar sequence as opposed to a tetrahedral sequence. So if we have palladium with kind of 2 generic, maybe Lewis base ligands, on the opposite side we must have, but on the same side of each other, on the opposite side of Lewis bases, on the same side of each other, we must have our 2 monovalent ligands that we hope to adjoin with each other. So these must be adjacent. In square planar terminology, not surprisingly, that's called cis. Then we can do reductive elimination to form our, if we started with palladium 2 plus oxidation state, we can now form our bond between our 2 monovalent ligands. So again, we don't know too much about the curly arrows, but we do know that if you position those monovalent ligands to be trans to each other, we don't see reductive elimination occurring. And intuitively, that kind of makes sense. If you look at the complex of a square planar complex where the 2 monovalent ligands are trans, we won't see reductive elimination occur. Okay, so we've covered 4 of the reactions for the most part. We'll look at some more details of ligand substitution reactions as they come up in more specific settings. But we've seen ligand substitution, which involved dissociation, association. We've then seen oxidative addition, the important starting process for most transition metal catalyzed processes. And we'll look at those in a couple lectures. We've also looked at reductive elimination, the reverse of oxidative addition, that allows for the final forging of the critical bonds, which is what was the reason why we started with metal centers in general, was to form interesting metal bonds, typically in a catalytic sense. Okay, so that'll do it for this lecture. And we'll cover more of the reactions, migratory insertion and beta elimination in subsequent lectures. So until then, I'll see you next time.